All right, folks, we're back with more polar integration. Today, we've done so far polar coordinates and polar functions. Now we want to go into integration. So I'm going to give the setup of polar integration in terms of the Riemann integral. What we're trying to do is if you have a function defined, if you have a polar function and you're interested in the area of this function between theta equals alpha and theta equals beta. So maybe this function is going all around the place, but I'm just interested in between the angles alpha and beta. Okay, so I cut it out. So what we're going to do is we're going to kind of try to do lots of pi slices. So I'll do one pi slice like here. I drew it. There would be another one. There would be another one. There would be another one. Instead of doing rectangles for rectangular coordinates in the Riemann sum, we're doing pi slices, okay? So we're gonna do lots of these pi slices, and we're gonna look at what happens when the number of pi slices goes on to infinity. Okay, so I blew this picture up. I'm looking at this area here, so I'm estimating the curve on this piece. Now it's got some extra pieces. It's missing some area. It's missing this, but as the slices become thinner and thinner, they're almost going to be no error. There is going to go to 0. So what we're going to say is we want to calculate the area of this pi slice. So let's call this angle theta, okay? And if we did this for n pi slices, the kth one, you pick the radius. You just want it between this angle and this angle. Let's call it theta k. And we just pick the radius here, okay? Remember the function is r equals f of theta. So the radius here is going to be the distance from the origin is going to be f of theta, the theta star k. Okay. So what would be the area of this pi slice? I think the area would be 1/2 r squared theta. And the reason is, let's quickly go over why that is. If we wanted to get the area of a full circle with radius r, that would correspond to, you start from here, go around 2 pi radians, you get the full circle, and for 2 pi radians, you would get pi r squared area, okay? Now, I don't want to go around all around, I just want to go take this piece, okay, this theta piece here. Because that's the area that I'm going to calculate. So for theta radians, how much area would I get? For 2 pi radians, I would get pi r squared. For theta radians, well, we got to divide by 2 pi and multiply by theta. So when I get that, we get 1/2 r squared theta. So when we have a lot of these guys, okay, a lot of these guys drawn, so maybe we can draw another one. Maybe the next one would look something like this, okay? And so on. If we have lots of these ones, I can approximate the area of this polar region up here as k equals 1 to n. I have n pi slices. Area of each pi slice. How much was the area of each pi slice? It was 1/2 r squared. Well, I picked some angle inside that interval, so that's going to be f of theta star squared times the change in the angle. So I call it delta theta k for the kth pi slice. Now we want to define the area of this. I'm going to assume that each of the slices has the same change in angle. As n goes to infinity, we want to add all of these areas up. Now, if we notice, that's just the Riemann integral definition of a is equal to 1/2. Pull the 1/2 out, and this would be, well, it's alpha to beta f of theta squared d theta. So that was f of theta was r, so you can remember it as r squared d theta, or let me just write here so you can see it again, 1/2 alpha to beta f of theta squared d theta. Okay, so this is a nice formula. It gives you how to calculate areas of polar regions. Okay, so to recap, again, we have some big polar region. We want to draw many pi slices inside it, okay, and find the area of each pi slice and add them all up to get an approximation for the whole area. Okay, now each pi slice is going to have this change in angle. Let's call it delta theta. Okay, and whatever the radius we pick in that proper interval. And then the area of the pi slice is going to be 1/2 r squared theta. In other words, it's going to be 1/2 f of theta squared theta. Okay, so actually I should write this. Okay, changing the angle. All right. So instead of r, you can just plug in f of theta if you'd like. At the end of the day, once we did the Riemann integral, which is not very interesting for the engineers out there, it's probably more interesting for the mathematicians, you end up with this integral over here. Okay, so we get a nice formula. Now, formulas are not much good if we don't apply them to some problems. So I'm going to start off really easy. Okay, and we're going to try to calculate the area of a circle with radius c. Now, I didn't say radius r, I said radius c because remember r is the distance from the origin. It's not the radius of anything, although we frequently say radius for r. Okay, so I didn't want that to be confused. I just wanted to say c because when we do multiple integrals in multivariable calculus, you do have dr d theta, not to be confused. Okay, so the radius is length c. So here I drew a picture. We have a circle of radius c. Now the area is 1/2 0 to 2 pi r squared d theta. That's the formula. Okay, now why is it 0 to 2 pi? Think about it. We're gonna sweep. We're gonna start from here, and how long would it take for me to go around the full circle? How long would it take me to sweep? I need to go around 2 pi radians. If I wanted to do a half a circle, I would need to go around pi radians. Okay, so how long does it take to sweep from the origin? Okay, think about the rays coming out like this. Okay, and it takes you will sweep it when you go around 2 pi radians. Okay, so it's going to be 1/2 0 to 2 pi. My r was equal to c squared d theta. Okay, so now we're going to integrate it, and once we integrate it with respect to theta, we get 1/2 c squared theta. Now a frequent mistake here is instead of writing 1/2 c squared theta, people write c cubed over 3 here. Okay, it's not c cubed over 3. C is a constant. We're integrating with respect to theta. We're not integrating with respect to c. So that's very important to keep in mind. So this is a constant. So the integral of a constant is constant times the variable. The variable here is theta. So we have c squared theta. There was a 1/2 there. Plug in your 2 pi, and the 2 pi's and 2 is going to cancel. When you plug in 0, you get 0, of course. So you get pi c squared. So this is the area of a circle that we've known since elementary school. If you have seen how to do this in rectangular coordinates, it takes quite a while when you try to do trigonometric substitution. Okay, when you're doing this in rectangular coordinates, when you're trying to find the area of a circle in rectangular coordinates, this is a lot more involved. Okay, so it becomes a lot more involved. And when you do because the circle is very circular, okay, that's the reason we're using this polar coordinates here. It makes the integral much easier. Okay, trust you and me, if you did the rectangular integral, it would take quite a long time. Okay, so let's move on to something more interesting. I would like to find the area of r equals 1 plus cosine theta. Now, in our last vid, we saw how we would draw this. You just plug in angles. When you plug in 0, cosine 0 is 1, so the radius is 2, so you're out here, okay? And let's, for example, plug in pi over 2, then this is 0, so r would be equal to 1. So you're continuously going to 1, and then when you're at pi, it would be cosine theta would be minus 1, so r is 0, so you're back at the origin. You got this heart shape, it's a cardioid, okay? So we'd like to find the area inside this cardioid. Now, to find the area, again, think about rays going out. I'm always at the origin. So I'm an air traffic controller at the origin. That's how we set up the polar coordinates, remember? And how long would it take me to go around and calculate this? We'd go around like this and like this. So it would take me, again, 2 pi radians to go all around and capture all the area. Okay? So if we set up the integral, don't forget your 1/2. It's going to be 0 to 2 pi, the function squared d theta. Okay, so just so that we can see how this is done, one example. one thing that I did was, I'm trying to be smart about here now. Now, instead of going 0 to 2 pi, I can just go halfway around 0 to pi. So I can do the top half and multiply by 2 because the region is symmetric around the x-axis. So that, if I multiply by 2, that would get me, so if I can do it from 0 to pi and multiply it by 2, so I would get rid of this 1/2, but I'm just doing half the cardioid. Okay, so 1 plus cosine theta squared, we open it up, we get 1 plus 2 cosine theta plus cosine squared theta. Okay, now this bit is easy to integrate. It's going to be 0 to sine theta, evaluate from 0 to pi, plus I've got this integral. Okay, now if you remember, cosine squared was equal to 1/2 1 plus cosine 2 theta. Okay, so that was a neat formula that helped us reduce these cosine squared integrals. Otherwise, you wouldn't be able to do it. So I used it. Instead of cosine squared, I plugged in 1/2 1 plus cosine 2 theta d theta. And what do we get? Well, from here, from this piece, pi minus 0, sine pi, sine 0, they're all 0. So from this piece, I get a pi. And from this piece, I'm going to get 1/2 theta plus 1/2 times integral of cosine 2 theta is going to be sine 2 theta over 2. And this is going to be from 0 to pi. Well, the nice thing here is when you plug in pi, you get pi over 2. Sine of 2 pi is 0. And sine of 0 is 0. So that's gone. That's gone. So it's just pi plus pi over 2 is 3 pi over 2 is the area. Okay. So this would be a standard calculation. Let's do something more difficult. I thought of doing something more difficult. And let's do an intersection problem. So the way we're going to set this problem up is, I'd like to find the area inside. Remember, this is going to be a circle. R equals 3 cosine theta. It's going to have, it's going to be on the x-axis. Okay. The center is going to be at 1.50 right over here. Okay. I want it inside the region, inside this circle, but outside this cardioid, 1 plus cosine theta. So the first order of business is I drew both of them. Okay. So this doesn't look much like a circle. I'm sorry, that's my bad. It's supposed to be a circle. And this is the cardioid, okay? The cardioid we were just talking about a few moments ago. Okay, so we said inside the circle, outside the cardioid, so it's got to be this region. Inside the circle, outside the cardioid, it's going to be this region. The first thing I need to do is figure out where these guys, at which theta, these guys intersect. Okay, I need to find this theta where they intersect. Okay, so to do that, I'm going to set the equations equal to each other. So I'll set 3 cosine theta equal to 1 plus cosine theta. So once we do that, we get 2 cosine theta is equal to 1, and which is going to imply that cosine theta is equal to 1/2. That means theta is going to be pi over 3 radians or minus pi over 3 radians. Okay, so here's the picture redrawn. Where they intersect is at pi over 3 and minus pi over 3. Okay, so for this problem, we're just going to set up the integral. I'll let you guys finish it up if you want to on your own. I'll just set up the integral. Well, what's going to happen here is we have our 1/2, the standard 1/2, and the region that we're interested in starts from, the rays that we're interested in starts from where they intersect, which is minus pi over 3 radians, and we go all the way up here to pi over 3 radians, okay? And we want to do the outside minus the inside. Well, the outside is the circles. The outside area would be the circle squared. And the inside area is the cardioid squared, okay? The theta. Now, again, we're going to use symmetry. Instead of calculating this whole area, I can just calculate this half area, okay? So all I need to do is go from 0 to pi over 3. And if I multiply it by 2, I would get this whole area, right? Because it's symmetric around the x-axis. So I'll just calculate the upper half. And multiply it by 2. Well, once I multiply by 2, I get rid of this 1/2. So it's going to be 0 to pi over 3. The outside one is the circle squared minus the cardioid squared d theta. And you can finish that on your own. It's not very interesting. The setting up of these guys is important than actually solving them from our perspective. Okay, so again, let's go over this very quickly because the next one is going to be even harder. we have this circle and we have a cardioid, okay? The first thing, we want to find the area inside the circle but outside the cardioid. So I drew that in, shaded that in. And the first order of business is we need to find the theta where they intersect, the angles where they intersect. So we set them equal to each other. We solve for theta and we get plus or minus pi over 3. So that's 60 degrees. Plus or minus 60 degrees is where they intersect. Now, again, I'm imagining these rays going out, okay? Starting from minus pi over 3 all the way to pi over 3. So the outside minus the inside area, okay? So it's going to be squared minus squared. It's not the difference squared. It's the bigger area minus the smaller area. So the circle squared minus the cardioid squared, okay? And then we use symmetry instead. So we calculated just half the area, multiply it by 2. So I can do 0 to pi over 3 and get rid of this one half, which makes it a little nicer to handle. Okay, so let's make this even more difficult. Okay, even more difficult. And right now, I'm going to change the question. We're going to again have the same curves. We have the same curves, r equals 3 cosine theta and r equals 1 plus cosine theta. But this time, I want the area inside both of them, okay? I want the area of their intersection. So this is the region inside both of them, okay? You see this kind of region here. This is the region inside both of them. So from the previous problem, we know that they intersect at pi over 3 and minus pi over 3. So I'm going to do the same trick. I'm going to, instead of calculating this whole area, I'm just going to calculate the upper half, okay? And then multiply by 2. That's going to let me get rid of this 1/2 over here, okay? Now, 0 to pi over 3, it's very important. When we're sweeping, I want the area inside both of them. So think about this. I'm sweeping with these rays, okay? And what are the rays touching? They're touching the curve r equals 1 plus cosine theta when theta is between 0 and pi over 3. You see, again, just draw the real rays out, okay? And they are touching not the circle, but the cardioid, okay? From pi over 3 to pi over 3 to all the way to pi over 2, okay, to 90 degrees basically, from 60 degrees to 90 degrees, they switch curves. Instead of touching this cardioid now, they start touching the circle, right? If you draw these guys out, they are now on the circle, okay? Not on the cardioid. They were on the cardioid, they switched. So what we're going to do is, my rays are touching 0 to pi over 3, they are on the cardioid, so I'll do the cardioid squared. And from pi over 3 to pi over 2 radians, okay, they are not on the cardioid, but they are on the circle, so I'll do the circle squared. Okay? So interesting. Always, if you get confused, always trace what the rays from the origin are going to touch. They are touching the cardioid, then they're switching over to the circle. Okay? Now, I want to end up with one single question. Okay? I'll let you guys try to work this out. I want you guys, so this is interesting, find the area inside r equals 2 cosine theta, okay? So it looks like a dumb question, but it's not. There's a point to this question. R equals 2 cosine theta, remember that was just a circle centered around x equals 1, right? It's just this circle, and here is 1, and the radius of it is 1. So it's a circle with radius 1, which is pi r squared, the area is pi r squared, the area has to be equal to pi, right? Okay, we know the answer before we start, because I want you guys to know the answer before you start, in case you set up the integral wrong. Now, this is a very interesting because drawing this circle was kind of interesting, wasn't it? When you start doing this, a bad thing to think would be, okay, I'm going to go 0 to 2 pi, the circle squared, and that's going to be the answer. I'm going to multiply it by 1/2. That's the wrong answer, okay? So if you think, let me write it clearly, area is not equal to 1/2. I'm saying not equal to 0 to 2 pi, 2 cosine theta. If you think this is the angle, this is the answer, this is not right, okay? The reason is, it doesn't take you 2 pi radians to go around the circle, but as we've seen in last class, it actually takes you just pi radians, right? If you go from 0 to pi over 2, trace with your hand or your pen, you get the upper circle. And then we saw it last class, when you go from pi over 2 to pi, all the radiuses are negative, so you got the lower circle, okay? So it just takes me, what I'll do is I'll calculate the area of the top, okay, and then multiply it by 2. So the area is actually twice 1/2, okay? So it just takes me, watch my fingers, it just takes me pi radians to go, pi over 2 radians, just 90 degrees to to trace the upper circle. So the answer is 0 to pi over 2, 2 cosine theta squared d theta. Okay, if you do that, if you do this one, you're going to get twice the circle. If in 2 pi radians, you actually go around the circle twice. Okay, so you get twice the area instead of a single area. Okay, so that's all I wanted to do with polar integration. There are much harder problems that you can try your hand at. You can try to find, looking at a calculus, you can try to find these pretty flower shapes. You can try to find their areas and whatnot. And these are going to be especially helpful when we do multivariable calculus later on. Thank you for listening. Bye-bye.